All right, so we are doing problems from chapter 17. Okay. This problem says the displacement of air molecules in sound waves is modeled with the wave function sxt is equal to 5 nanometers. So there's the amplitude of oscillation. Cosine, there's the wave number x minus omega t. Okay, so here's the standard form. There's the amplitude cosine kx minus omega t. Okay. So before we start the problem, let's talk about a few things. So this is sound waves in air. Okay, sound waves in air. What kind of waves are they? Are they longitudinal or transverse?
It's longitudinal.
Yeah, yeah. So in fluids, it's longitudinal waves. So the wave is traveling in this direction. The particles are oscillating parallel to the direction of travel. Okay. All right. So this is giving you the displacement of the particle from its equilibrium position. So there's the equilibrium position of an air molecule, and it's oscillating like that. All right. Now, before we go into this, so here's the amplitude. The amplitude is 5 nanometers. Okay. Does that number mean anything to you guys?
That's to the -8 of a meter.
So nanometer is 10 to the minus 9 meters. Okay. So roughly, the size of an atom is about 1/10 of a nanometer. Okay, so here's an air molecule whose amplitude is about 10 times the size of the molecule. So that's how it's oscillating. Okay. All right. So now let's solve the problem. So what is the wave speed of the sound wave? Okay, so the wave speed is this speed that they're talking about. Okay, so there's a couple of speeds. The wave speed is the speed at which the wave travels. Okay, and then these air molecules are oscillating, and their speed is changing. So like you can imagine a mass attached to a spring. Those molecules are oscillating. So we'll talk about that speed, but this is the wave speed. That's the speed at which the wave is traveling. Okay. And the wave speed is given by omega divided by k. Okay. And so if you look at this expression, there's omega 3.4 times 1/4 times 10 to the 4 per second. And k, the wave number is that 91.54 per meter. Okay. And the meter will go to the top and the second will come to the bottom, so the wave speed will be in meters per second. Okay, 343 meters per second. Okay, so what is the maximum speed of the air molecule as they oscillate in simple harmonic motion? Okay, so we can think of a mass attached to a spring, and let's say this is the equilibrium position, and it's oscillating back and forth between these two points, okay, these two extremes. When is uh, the velocity of the speed of the mass the maximum? At the equilibrium point, okay? So just like that, this will be at the equilibrium point, okay? And if you guys look at the expression, so the speed, the maximum speed of this guy is speed of the molecule. Of the molecule is A omega, okay? And you get that from this fact. So del x by del t, del s by del t is, you guys remember this? This is a partial derivative. You're taking the partial derivative of s with respect to t, and you're treating x as constant, okay? So derivative of cosine is minus sine, and then you get a minus omega from there. So it would be A omega sine kx minus omega t. And the maximum value of this would be correspond to this being 1, so the maximum value would be A omega. Okay? And that's what I've written here. Okay? So there's the amplitude. The amplitude is 5 nanometers. And there's omega. Okay. So the molecule's maximum speed is A is 5 nanometers, and omega is 3.14 into 10 to the 4 per second. And so this works out to 1.57 into 10 to the power 5 nanometers per second. And a nanometer is 10 to the minus 9, so 10 to the minus 9 and 10 to the 5 is 10 to the minus 4, so 1.5. Meters per second. And what I'll do is I'll absorb one of those in 10 to the minus 1 here, so I'll write this as 0.157 millimeters per second. So that's how fast the air molecule is moving, the fastest speed of the air molecule when it's oscillating. Okay. Did you guys understand that? Okay, so what is the speed? Okay, as the air molecule is oscillating at the equilibrium position, when it's going the fastest, it's going about 1/10 of a millimeter per second. Okay. And that speed is different than the wave speed. The wave speed is, how fast the wave is traveling, which is 343 meters per second. All right. What is the magnitude of the maximum acceleration of the air molecule? Okay. So again, having this analogy in your head is good. When is this guy accelerating the greatest? I'm sorry? At the extreme points. Okay. And if you look at your notes, the acceleration, maximum acceleration corresponds to A omega squared. Okay. So, and that would be del S squared by del T squared. Okay. So So acceleration comes from here, del square s by del t square. And so if you take the derivative of this again, it's sine is cosine, derivative of sine is cosine, and then you get a minus omega here. So this is minus a omega square cosine kx minus omega t. And the maximum value of this will be a omega square. So, and that happens at the extremal points. So that's 5 nanometers. All right. Okay, it's half a g. Okay, what that means is the restoring force when the molecule is at its extreme, the restoring force is equal to half the weight of the molecule. Okay, the force with which this spring is pulling it back is equal to half the weight of the molecule. That's what that means. Okay? All right. So this next problem says bats use sound waves to catch insects. Bats can detect bats can use frequencies up to 100 kilohertz. Okay, so here's the velocity of speed of sound. Okay, and as the frequency goes up, the wavelength goes down. Yep. And you guys know, so so if you want to see an object, okay, so if you're using this wavelength, okay, so if this is the smallest wavelength you're using, this is the smallest object you can see. Okay, so if you want to see smaller and smaller object, you have to use higher and higher frequency. Okay, so if this particular bat uses frequencies up to 100 kilohertz, there's the smallest insect it can see. Do you guys understand that? Okay. If the sound wave travels through air at a speed of v equal to 343 meters per second, what is the wavelength of the sound waves? So we'll see what is the smallest wavelength. Okay, so (100 kilohertz). Hertz is 1 over second. So this is 10 to the 5. Okay, so this would be 3.43 times that. So the wavelength is 3.4 millimeters. So the smallest bug it can see is about 3 millimeters. Yeah. Yeah. So here's a sort of a story, I guess. So in this forest, a big bat lives and a small bat lives, and they don't bother each other. I mean, this is real. So what's happening? The big bat obviously is eating big bugs. Okay, so the big bat uses low frequency, okay, frequency 60,000 hertz. And the small bat uses frequencies of 100,000 hertz for echolocation. the higher the frequency, the lower the wavelength, and you can see small bugs as well. You can see big bugs as well, but you're not going to eat the big bugs that that the other guy is eating. Okay? So you can peacefully coexist. You guys understand? All right. What is the speed of sound in a medium where a 100 kilohertz frequency produces 5.96 centimeter wavelength? Okay, so hertz 5.96 into 10 minus 2 meters. Okay. So that kills that. So it's and 5.96 times 10 to the power 3. So okay, so the speed is about 6,000 meters per second. So it's well, okay, so it's not in air in gases it's about 300 meters per second. In liquids it's about 5 times faster, and in solids it's about 10 times faster. So there, the medium is steel through which, okay. Yes, so the speed of sound, if it's 1 units in gases, it's in liquids it's about 5 times greater, and in solids about 10 times greater. Okay. The density of a sample of water is 998 kg per meter cube, and the bulk modulus is 2.15 gigapascals. What is the speed of sound through this sample? Okay, so again, this is a fluid, so it's longitudinal waves, and the speed of sound is given by that. Okay, bulk modulus divided by density. 2.15 gigapascals, and density is 998. Okay, so the speed of sound is that, and you can check that in here. So water, there's the speed of sound, 1480 meters per second. Okay. You guys understanding this? The warning tag on a lawnmower states that it produces a noise at a level of 91 decibels. What is this in watts per meter squared? Okay, so this, they're asking you for the intensity. And the decibel scale is related to the intensity, like so. I naught is the intensity, is the threshold of hearing. Okay, so that's the lowest intensity you can hear, and that's 10 to the minus 12 watts per meter squared. And actually, that, do you guys remember the lowest frequency? I mean, what is the frequency your ears are most sensitive to?
Low
What is the, huh?
Was it like 20,000?
No, the hearing range is 20 to 20,000 hertz. What I'm asking you is the following. So you see this graph? This white area is what you can hear. See, you're most sensitive to this frequency, about 3,500 hertz. Okay. All right, so this is the threshold of hearing. Okay. So the decibel level is 91 decibels, and you want to find the intensity of the sound. So 9.1 equal to log, okay, and then 10 to the power 9.1 equal to I by I naught. So you raise this to the power of 10 and you get that. So, and 10 to the power of 9.1 times I naught equal to I. So I and I naught is 10 to the minus 12. So the intensity is that 10 to the power of minus 2.9. Okay? And if you like, you can calculate this. And this is equal to an 8-hour exposure of sound to a sound intensity level of 90 decibels may cause hearing damage. Okay, so if you listen to something at 90 decibels for 8 hours, okay, so, and now you know why rock stars have bad hearing. Okay, most of them. So what energy in joules falls on a 0.8 centimeter diameter eardrum so exposed? Okay, so the radius of the eardrum is 0.4 centimeters equal to so 0.4 into 10 minus 2 meters equal to 4 into 10 minus 3 meters. So the radius of your eardrum is 4 millimeters. Okay. So so energy is, okay, remember intensity is intensity has units of joules, okay, per second per meter square. Okay, so if you wanted to calculate energy, it's time times the area. Okay, so the total energy falling on the ears is intensity times the area of the eardrum times how long that sound is falling on your eardrums. So this is the energy deposited on your eardrums over the 8-hour period. Okay? And we're going to find this guy from this 90 decibel sound level. Okay? So beta, the decibel level is, okay, so this is a 90 decibel sound. Okay, so 10 to the 9 is I over I 0. and I is 10 to the minus 12 watts per meter square. Okay. And so now we're going to put this in here. Okay. So what this is saying is, again, a 90 decibel sound, you're continuously hearing it for 8 hours, and how much energy was deposited on your eardrum. Yeah. All right, so the energy deposited is intensity times area of your eardrum times the time. Okay, so this was 10 to the minus 3 watts per meter square. Area of your eardrum is pi r square. R was 4 times 10 to the minus 3 meters square. And 8 hours, each hour is 3,600 seconds. Okay, so this is how much energy was deposited on your eardrums. Okay. All right, let's take care of ours. This is 10 to the minus 3, 10 to the minus 6, so that's 10 to the minus 9. And then we'll absorb 3 from here, so 10 to the minus 6. Okay. And energy, this will be in joules. Pi, there's 4 square, which is 16. And then there's an 8 and a 3.6. Okay. So that's how much energy was deposited. So it's 1.45 millijoules. Okay. So let me give you a sense for this. Okay, so energy is equal to mgh. This is potential energy. So G is 10. So if you drop 1 gram, 1 gram is 10 to the minus 3 kgs. If you 10 to the minus 3 kgs, G is 10 from a height of 0.1 meters. So if you drop a 1 gram object from a height of 10 centimeters on your eardrum, that's how much energy was. Did you guys understand that? But what is causing the, well, okay. Anyway, I don't know how the damage actually happens. So imagine something, this is vibrating 8 hours, All right, so loudspeakers can produce intense sound with surprisingly small energy input in spite of their low efficiencies. Calculate the power input needed to produce a 90 decibels sound intensity level for a 12 centimeter diameter speaker that has an efficiency of 1%. This value is the sound intensity level at the speaker. Okay. So, so right at the speaker, I guess, so you're going to listen to the speaker right next to it, okay? That's what they're saying. So the efficiency of the speaker is 1%. What does that 1% mean?
99% is heat.
Very good. So 100 joules of electricity and you get 1 joule of sound. Okay? And the other 99% is heat is all right. So calculate the power input needed. Okay, so input power, let's say, is that, and the power in the sound is 0.01 input power. Okay. Intensity is power of sound divided by area of the speaker. So you're listening right next to the speaker. And area is, this is a 12 centimeter diameter speaker, so power of sound by R squared. Okay. Well, let's first calculate the intensity. What was the sound level right next to the speaker? It's 90 decibel. Again, we've done this a zillion times now, so I'm just going to this is 9 log of I by I naught. So 10 to the power 9 is I by I naught. And I naught is 10 to the minus 9, 12. So I is 10 to the minus 3 watts per meter squared. All right, so now we're going to put that in here. Okay. So the energy per second in the sound is intensity times pi R squared, 10 to the minus 3 watts per meter squared, times pi. R was, what is R?
6 times 10 to the negative second meters.
Very good. Okay. So that's 10 to the minus 4, 10 to the minus 7. So 36 times pi, 10 to the minus 7 watts. Okay. So this is the power in the sound, and remember the speaker was 1% efficient. Okay, so this is the sound. So the power input in electrical energy is P sound divided by 0.01. So input energy is P sound over 0.01. So what this is saying is, so this is your electrical energy. A milliwatt speaker, if you stick your ear right next to the speaker, you're getting a 90 decibel sound. Yeah, that's what that means. So this problem says, what is the fundamental frequency of a 0.672 meter long tube? So that's a 2 feet long tube, open at both ends on a day when the speed of sound is 344 meters per second. Okay, so this is a tube open at both ends, and the fundamental frequency is the lowest frequency of oscillation. Okay, and the fundamental frequency corresponds to, so for a tube open at both ends, it's node in the middle, and antinodes at the ends. And okay, so you can here are the fundamental modes. So here are the frequencies for a tube open at both ends. This is the fundamental mode, meaning the lowest frequency it can vibrate at, air column. And this is the next higher frequency. So the frequencies are given by integer n times v over 2L. Okay. So we want F1. So F1, the fundamental mode is V is 344 meters per second. And the length of the tube is
Where did we get the integer from? What is
oh,
You said it was 1, but I'm not quite understanding what the integer actually represents.
the frequencies at which it can oscillate are integer multiples of this. Okay. So you can think of the integers as the nodes. 1 node, 2 nodes, 3 nodes.
Okay. So if you want to oscillate more times, you add more integers.
These are higher frequencies.
Frequencies.
Yeah.
Okay.
So if this is a flute and that's the length of the flute that you're using, the lowest frequency it will oscillate at, the lowest frequency sound it will produce at a large amplitude corresponds to this frequency.
Okay.
The next higher frequency will be this.
Mhm.
The next higher frequency will be this. Those are pure tones. But actually, if you played a flute, the sound that's produced is an admixture of all these guys.
Okay.
You can never just excite that or just that or that.
So each time you bump up the integer, you're working at a higher frequency for that same too.
Mhm, mhm.
Okay.
Mhm.
That makes sense. Thank you.
These are called, this is they're called the harmonics.
Mhm.
A drum head doesn't do that. You saw it. All right, so what did we say this thing worked out to? 256 hertz. Okay, so the next higher frequency this flute could oscillate would be 512. Okay. The next higher frequency would be 768 and so on. Okay. So F2 would be 512 hertz. F3 would be 768 hertz and so on. Okay. So what is the frequency of the second harmonic? There is the frequency of the second harmonic. Okay. And there is the frequency of the third harmonic and so on. Okay, this problem says a piano tuner uses 512 hertz tuning fork to tune a piano. He strikes the fork and hits a key. So the fork is producing one frequency, and when you hit the key, when you strike the key, you're producing another frequency. Okay. Now the idea is the following: if the two frequencies match, then you won't have any beats. If the frequencies don't match, then you have beats. Okay. He strikes the fork and hits a key on the piano, and here's a beat frequency of 5 hertz. What does a beat frequency of 5 hertz mean? What does it mean? What does a beat frequency mean? What do beats mean anyway?
It's like the difference between when the sounds hit your ears, like in the time they're traveling.
No.
Is it a different amplitude of wave?
Very good. So when you place two sounds, the intensity level will go up and down. And if it goes up and down 5 times a second, that's 5 beats. Okay? All right. So the beat frequency is the difference in two frequencies. Okay? So if one frequency is 5 times above the other, you hear 5 beats, and if one is 5 times below the other, you still hear 5 beats. Okay? All right. By the way, so the velocity on a string is given by that. A piano is a stringed instrument. Okay, the keys are hit to excite the string. Okay, now if you remember, so velocity is frequency times wavelength. Wavelength depends on the length of the string. So when you're changing the tension, you're not changing that. If you increase the tension, what you're doing is you're increasing the pitch of the string. You're increasing the frequency. All right, so now let's read this. So he tightens the string of the piano and repeats the procedure. Once again, he hears a beat frequency of 5 hertz. Okay, what just happened? So he tightened the string, so he increased the frequency of the string. So initially it must have been below the tuning fork, and then once he tightened the string, then it went up to that. Okay? So the piano frequency, initial piano frequency must have been 512 minus 507 hertz. And the final piano frequency must have been 512 plus 5. Did you guys understand that? Okay. At an air show, a jet flies directly towards the stands at a speed of 1200 kilometers per hour, emitting a frequency of 3500 hertz on a day when the speed of sound is 342 meters per second. What frequency is received by the observers? What frequency do they receive as the plane flies directly away from them? Okay, so here's the perceived frequency, here's the speed of sound, here's the observer's speed, well, I say speed, so here's the formula. This is 342 meters per second. Okay, so the source is moving, the observer is at rest, V0 is 0, okay, so V is 342 meters per second, observer is at rest, and the source, okay, source speed is, well, let's, so 1200 kilometers per hour, kilometers is 1000 meters, 1 hour is 3600 seconds. So you divide that by 3.6 to get that speed in meters per second. Okay, so this plane is flying fast, but it hasn't broken the sound barrier. Okay. All right. What is the sign convention for these guys? When you're moving toward each other, then these guys are positive. Okay. So here's the observer, here's the plane. When he's flying towards the observer, Vs is positive. Okay. So Vs is positive. Okay, so so for part A, the frequency is V over V minus Vs times F. 342, 342. When the plane is moving toward the observer, that's positive, so minus 333.3 meters per second times this. So the perceived frequency So what is this saying? The perceived frequency is 40 times greater than the emitted frequency. Okay? And this is equal to the emitted frequency was 3,500 hertz. So there's the 137,500 hertz. Will you hear this? No. So it's above your 20,000 hertz hearing range. Okay? So the lower frequencies, well, so you won't hear it. But there are enough lower frequencies that will remain within your hearing range. Okay? So how do we calculate this? So anything, so 20,000 divided by 40 equal to, 500 hertz. So all the frequencies emitted below 500 hertz that the plane emits, those you can hear. Those will get shifted to still within your hearing range. Okay? All right, what happens when the plane moves away? So here's the observer. Now the plane is moving away. Okay, now when the plane is moving away, then that speed is negative. Well, that velocity is negative. Okay, so once the plane passes you, you can hear those frequencies. An airplane moves at Mach 1.2. What does that mean?
1.2 times the speed of sound.
Right. Okay. And produces a shock wave. Okay, so here the plane, so there's the plane moving in this direction, and this angle is called the shock angle, and the shock angle is given by the speed of sound divided by the speed of the source, or the plane. We'll call it the plane. And again, you guys understand that this equation only has a solution when the speed of the plane is greater than the speed of the sound. Okay? So, and V over Vp is Mach number. No. Vp over V is equal to Mach number. So the speed of the plane is 1.2 times the speed of sound, 1.2 times 343 meters per second. So that's 343 meters per second is the speed of sound at the temperature in this room. At 20 degrees Celsius. Okay, so that's the speed at which the plane is flying. And what is the angle that the shock wave moves? So theta is sine inverse V by Vp. Sine inverse 1 over 1.12. 1.2. So it's 56 degree. Okay, so watch this equation. Faster the plane is flying, smaller this number, and smaller this angle. Okay, so if you see pictures of shock waves, okay, so you might see a picture. Just Google shock waves, and you'll see several images. Okay, so this guy is flying faster than this guy. Okay. All right.